Okay, well, I'm not seeing anything here, but so I'm going to be speaking about Pydantic today. We recently released V2. It's a quite popular library for data validation. The talk today is going to be a little bit, there's going to be a quick introduction to Pydantic, a quick introduction to some of the things we changed in V2, but really what I want to talk about is kind of what goes on internally, how we interact with the type system, and how we're interacting with Rust, which we use as a big part of it. It was a big part of the reason to rewrite V2. So this is the basics of what Pydantic does. It's kind of a DSL and built into the type system. It lets you use types to declaratively define schemas that can then be used to validate data and serialize data. So in this case, if you have a user with a name and age, you can say the name is a string and the age is an integer. And you can validate JSON data, you can validate Python data. And if it's invalid, it'll give you some nice errors. And this is used by Fast API, for example. It's one of the most popular uses of Pydantic. You can say, this is my input data for my API, this is my output data, and it'll make sure that the input data is valid, and it'll serialize the output data as you defined it. Those are basic usages. So what did we change in V2? One of the things we made a lot easier is working with non-object data. So Pydantic V1 was very based around like an object in a class. So we have this base model which still exists in V2 and you can use, but it was really weird to do things like saying my data is a list of something. You have to use this like weird root model construct, which ended up being both a class but also a type. We made a lot of that simpler with this thing called a type adapter, which lets you take an arbitrary Python type and say build a parser and serializer for it. So now you don't have to have kind of a root model thing. You can just have the type around, and wherever you want to serialize and deserialize it, you can just throw in a type adapter. So in V1, this is what the root model kind of looked like. You can see it's kind of a class, but then it kind of acts as a list of things. And in V2, you just have the type and you wrap it in a type adapter. This also gave us much better support for type-dic and data classes. So one of the common requests is like, I don't want to use Pydantic everywhere. I want it someplace, I want to like mix and match. Like some place I want to validate, some places I just want data classes. And now you can do that a lot easier because you can just use data classes everywhere. They work in a fast API endpoint, but also if you want to validate a data class in an arbitrary point in your code, you can use this type adapter thing. Most things work pretty well. One of the things that like type checkers still don't like is they don't like that Pydantic config thing on a type-dic. A lot of them will yell at you even though it works at runtime. It didn't work at runtime until recently, but now it does. So there's improvements being made, but there's still some like rough edges of like trying to force this static typing into runtime typing. Another thing we introduced is wrap validators. Pydantic always allowed you to insert arbitrary Python functions into your validation. And now we let you do more complex things because you can insert a function that calls Pydantic's validation and then catches an exception or just skips it in some cases. So like in this case, we can have, if you have like a function that parses a number to something human readable, let's say, I don't know, you have like an expensive LLM to parse that. And you don't want to call it every time, so you could say, okay, Pydantic, you try and validate the number, and if it's like just a digit one, it'll work, and if that fails, then I'll call my expensive function. So you can do it, you can call it beforehand, like if you say, if the string is equal to now, then insert datetime.now, don't try and parse it. Or you can catch an exception, or you can call it only in certain cases if your function is expensive. It lets you handle a lot more cases with arbitrary functions. So how does Pydantic V2 interact with the type system? Pydantic V1 had some weird things that didn't interact with the type system correctly. Like one of the prime examples, I think, was adding constraints to a list or a string or something. You'd call like a constr function in your type, and that would return to you an object which meant things to Pydantic, but meant absolutely nothing to the type system. So we have a MyPy plugin that tried to sort some of these things out, but like if you tried to use like that first name with VS Code or some other type checker, it would just yell at you and say like this, I don't know what this type is, and then your whole thing kind of breaks down. In Pydantic v2, we're using PEP 593's annotated. It's typing.annotate. It's also available in typing extensions, so it works for any Python version. But essentially, that lets you separate the type from metadata for runtime stuff, including Pydantic. So you can say, you know, I have, instead of doing this constr thing, you can say, okay, last name is a string, and you add some constraints. There's different ways to add constraints. There's field, there's annotated types. So that part needs a little bit more fleshing out and like kind of normalization across the ecosystem. Because you can see like here I'm importing from annotated types, and I'm also importing stuff from Pydantic, and it can be confusing as to which you should use, but it works a lot better with type checkers. And in fact, one of the things you can do now is you can link validation to a type. So if you want to do this sort of thing where you insert an arbitrary function to run, it used to be it had to be inside a base model class, and it's, you know, linked to a specific field, or you say it runs for all fields. But now you can actually link it to a type itself. And what that lets you do is you can like then import that type into multiple models using multiple fields, and it'll just work. So like in this case, I'm saying what I mentioned earlier of if the string is now, then return datetime.now. Don't try and parse it. And that's like something relative. I don't know that I recommend that, but relatively common. You just use datetimer now instead of datetime as your type annotation. And type checkers will look at it exactly the same. They're not like, oh, you know, you can pass in a datetime. It won't say you need to instantiate a datetimer.now object or something weird like that. It'll just totally ignore everything to the right of the type in annotated. You can also do generic constraints. So like in this case, I can make a constraint that's positive and a constraint that's even, and then I can even nest them together. So you can like compose constraints on types like that, and you can do that like type alias like this, so then it's kind of linked to positive even int, or you could do this within a field, so you can kind of mix and match, and it gives you a lot more flexibility as to, you know, what you want to bind validation to and how you want to compose things. Another really cool thing, and this was really something that was introduced by the typing community, was TypeAliasType, which is also kind of the default runtime construct for 3.12 and beyond, but is available in typing extensions, and essentially lets you make a named type alias. The previous type aliases we saw don't really have a name, and that's really important for supporting recursive types, because it lets you describe something like this, like my JSON, or you could just describe plain JSON, but in this case the thing I'm changing is instead of parsing floats as floats, I'm parsing them as decimals, which you might want to do because in JSON floats are just strings, so they have arbitrary precision, and if you just parse it to a float you could lose data, so a lot of people want to parse them to decimals. And just by using this little union type here, you can essentially build a JSON parser that parses 2 decimals directly. And if you try and get the JSON schema of something like that, you'll see with Pydantic v2 it's actually a correct JSON schema with like a recursive ref to itself that says, you know, it can be a list of itself and etc. So that kind of all works now with TypeAliasType, whereas before it was kind of shaky. Can I go back? Okay. So this is a really interesting use case. Jella, one of the typing folks, has a type checker that Poor uses called PyAnalyze. And PyAnalyze actually added support for annotated types, which is one of the ways to get those constraints on types. So there's now actually a type checker that it does runtime stuff, but it is a type checker where you can have these constraints. So you can have a type that you use in Pydantic that validates your deserialized JSON data, but you can also use a type checker to see that you're using those types correctly. And my understanding is that it can do pretty crazy stuff. Like you can even run arbitrary Python functions as a type checker to check that your data is valid for it. And so yeah, like in this case, that annotated stir literal only min len 1, that would also be valid within the context of Pydantic. So we're kind of getting to this place where this runtime metadata can be used by more than one thing. When it was just Pydantic's conint and an opaque object, only Pydantic knew what to do with it. And now it's kind of moving to a world where this information can be shared and can be used and is useful in multiple places. FastAPI also uses typing.annotated. Since last year, they've added support for this, so you can now use that, and it cleans up some things about the FastAPI experience, but it's also nice because you can kind of use the same paradigm everywhere to add metadata to your types. So what are some of the remaining pain points? So yeah, one of them is that you have to, I think annotated is quite verbose, like just to do something simple like this, like greater than, you have to import stuff, and I guess kind of, you know, if you saw it in my previous slides, it can get to be a lot of text. I think another interesting thing is with how Pydantic interacts with the type system is that, well, actually in this example, because I don't have my speaker notes, but yeah, the point here was string greater than 0. That just doesn't make any sense, right? Like it should be a statically detectable error that you typoed, but there is no way to detect that currently. No type checker can check those things. So you can make like apply constraints, and Pydantic actually does try to detect these things when it builds a model, but it can't always do it if you're like stacking a bunch of metadata on top of each other. So sometimes you'll end up with a runtime failure that says like can't compare a number to a string or something like that. And the other thing that you can't really be described currently is kind of this converter functionality, which happens in Pydantic a lot because by default Pydantic parses things. So if you give it a string 1, it'll parse that to the number 1 if your type annotation is an int. So it happens a lot that type checkers just don't like it if you have like an int field and you pass it a string, even though Pydantic will parse it and it works. Type checkers won't like that, and especially if you add your own function like this, which is, you know, doing arbitrary stuff at runtime. There's just no way to describe it with a type checker. So when you try and construct your types, you'll end up having to put type ignores in places. And I think there is a PEP for adding some sort of converter description of this sort of behavior to data classes only, but I think it'd be interesting to explore ways to add it in a broader sense, or at the very least add some way for type checkers to detect the simpler case that I had on this slide where you're just adding a constraint to a type that is not valid. And I think that should be quite doable. So I'm excited in general for us to develop better type safety around the stuff that goes into annotated. Now that it seems like it's being used more widely, I think part of making the user experience better will be to actually statically analyze that stuff. So delving into some of the internals of Pydantic is more like if you're just interested in how it works. And I think the funny thought I've had, and I'm not a compiler engineer or anything of the sort, is like, did we build kind of a Python to Rust compiler? And in some sense, we kind of did, because Pydantic starts with a type, a Python type, like a Python object, and you pass it, use it either in a type adapter or a base model or somewhere else where like Pydantic analyzes the type. We create like this intermediate representation of the type system, which is like a union of type dicts, and then from that we create a bunch of Rust objects. And the Rust objects are they look something like this, where we have some sort of trait, which is equivalent to Python protocol, give or take, and an enum, which is a union, and so yeah, we take Python types and create Rust objects that are statically compiled, because this union, it's not dynamic dispatch. This enum can only be one of several things, although we do have like cop-outs, like one of them is like kind of like this is any type, but the point is, yeah, we essentially take Python types and compile them into Rust thing. And in fact, someone was asking me the other day, why doesn't someone build a thing that does this? And I was like, well, that's actually what Pydantic does internally, but it's not all sun and rainbows, because there's, you end up having it ends up being verbose, and you end up having to make design decisions that you never thought of when you had to do it in Python. Like in Pydantic v1, to parse a string to an int, we basically called the int function on it, and we're like, okay, that does what it does, and we don't have to worry about it. Now in Rust, we have to decide if we want to extract it into an I64, or what do we do for larger numbers? And so we kind of like try to extract it to an I64, and if that fails, then we resort to extracting it to an unbounded size integer, with the idea that most integers are I64s, but then we don't want to fail hard if some of them aren't. So you end up with kind of a lot more logic and a lot more things to think about when you implement something like this in a lower language. And yeah, not all sun and rainbows, because although Pydantic v2 is a lot faster for runtime validation, one of the complaints we've gotten is it's slower to like import your models and to create these schemas, and that's because Pydantic v1 was lazy in a lot of aspects. Like when you ask it to validate something, it'd be like, okay, what's the type? And then go in and introspect there. Now we introspect everything at the beginning, and we build these Rust objects, so it's a lot more like kind of like the compiler thing. But then you have to wait for that to happen, and that can be expensive. And we've actually seen some people who had huge applications where it became a problem. Just importing was taking, booting up their web app was taking too long. Another really good advantage is that Rust forces you to have a lot clearer data structures. Because you have to, kind of everything has to be static and known at compile time. You have to be a lot more explicit with what your data structures are. You can't. Pydantic v1 had a lot of untyped any stuff going on internally, where it's just like iterating over types, and you can't really do that. So you have to really define your data structures. But the issue with that is then refactoring is quite difficult. Like if you have a large Rust code base and you want to change one thing, you'll find yourself having to change 20 files just so it'll compile, just so you can run it and see if your idea works. Whereas if you're developing in Python, one of the main advantages, or one of the huge advantages, is that you can just run a half-broken code base. And as long as it breaks where you know it was going to break, then it's fine. You can experiment that way. Another advantage of kind of writing stuff in Rust is that it forces you to have a clear separation between the different aspects of your program. So like for us, we have an intermediate representation of the type system, which is really nice because it's let us like operate on that instead of types. Pydantic v1 was kind of like all mashed together, introspecting types, creating Pydantic things, all kind of mashed together. Now we have kind of a clear separation. But because we have that clear separation, like once you're in like the world of I have some compile, some Rust objects, it's really hard to then insert dynamic behavior into there. And that's one of the things that users have struggled with V2 is, I want to insert this really dynamic behavior that's specific to my use case, and we've like created ways to do that in different places, but ultimately it's like a lot harder to go and say, okay, I have a new type. Like if you have a field that's an ABC or a protocol, then introspecting that type at runtime and creating a new schema for it can be difficult. And finally, Rust is lower level, which lets you do those sorts of optimizations, like saying I want to extract an i64 first, because I know that most things are i64s. But at the same time, you have to deal with a lot of lower level stuff. You have to deal with allocations, allocators, all that kind of stuff, and those things can be a struggle. We had at one point we found that the allocator we were using decided to allocate 10 gigs of RAM on some project that V1 only needed 100 for. And like finding that out, you only find it out through profiling and error user reports and things like that. So yeah, my suggestions, if you were gonna write something like Pydantic v2, where you have like some Rust extension and some Python stuff going on, would be to really think about and balance what you do in Python versus Rust. I would generally recommend to stay in Python, especially if you're a Python developer. Stay in Python as much as you can. Identify the hot hats and put that in Rust. Python is great to orchestrate things, and so yeah, try and avoid like super dynamic stuff in Rust and just orchestrate it with Python. I'd say also keep a clear design boundary between your Rust stuff and your Python stuff. Like I said, we have this sort of intermediate representation of the type system, which is just a type dict, and that was really good to be like the handoff between the two languages. And for performance, definitely minimize the back and forth between Python and Rust. Kind of design your thing so that you're not calling back and forth, because that's going to incur a huge performance hit. So like for Pydantic, inserting an arbitrary Python function will slow things down a lot, because we have to jump from Rust back to Python, back to Rust. And that's something to keep in mind. And that's all I've got. So I think we have like 3 minutes for questions. Any questions?
Is there any chance that the intermediate representation that's used in Pydantic making its way into some form of Python standard?
This is not
Yeah, so the question was, any chance of the intermediate representation that's used for representation of a Python type like nested structure, of that becoming something more open and standard? Right now it's kind of buried inside Pydantic.
Yeah, I think there's a lot of things that are buried inside Pydantic now that could have the potential to be more open and shared. And that's kind of what we were trying to do with the annotated types thing. I think that one's like in its current state, no, not really, because there's a lot of Pydantic specific things in that intermediate representation. But I think something like that could definitely be cool to have as a shared thing.
Thanks.
I guess we can have one more question. I guess it's all.
All right.
Thank you.
Thank you, everyone.